In addition to evaluating functions at a specific number, like we saw in the last few examples, we can also evaluate evaluate a function at a letter or an expression. Example 13 gives us an instance of this. We want to find f of a, given the function f of x is equal to negative 4x minus 2. In order to find f of a, we'll do the same thing that we did when this was a number in place of x. For every instance of x, we'll just replace it with the letter a. So our result will be negative 4a minus 2. Example 14 continues that idea, but now rather than just substituting an individual letter, we're substituting in an expression x plus h. So to find g of x plus h, for the function g of x equals x squared minus 4, we'll look for every instance of x and replace it with that expression x plus h. In this case, that means we'll get x plus h, that quantity squared, minus 4. Keeping in mind what that tells us is that we need to take x plus h times x plus h minus 4. We can FOIL that out to get x squared plus 2xh plus h squared minus 4. It's a good idea to get a fair amount of practice with evaluating functions at an expression rather than a number. That tends to be an idea that trips people up a little bit. But again, in this example, if we want to find d of x plus h, we're doing the same thing that we did when we wanted to find, say, d of 2. Everywhere there's an x in the function, we replace that with this new expression. That means we'll have 4 times the quantity x plus h squared minus 3, which will give us 4 times, we'll expand this out again, to get x squared plus 2xh plus h squared minus 3, and then we can distribute the 4 through those parentheses to get 4x squared plus 8xh plus 4h squared minus 3. Again, adding more letters into the problem can make things feel a little bit more difficult. So it's good to get practice with that, especially before we get to a question like example 16, where now what we're going to be asked to evaluate is the difference quotient. This very specific statement that's listed here is referred to as the difference quotient. For our purposes right now, it's a little arbitrary. It just looks like a really hard problem to evaluate. But practicing it now is going to be good because in calculus, the difference quotient is going to come back and be a kind of a critical foundational idea. So we'll get some practice with it now since it blends in with evaluating functions. But really what we're doing is just kind of prepping for something that you're going to see in calculus later on. In order to do this, we'll start off by finding n of x plus h, just like we did in the last two examples. We'll plug x plus h into that function to get x plus h squared minus 5, and then we'll subtract n of x, so just the original expression with no changes. And what we'll do is put that inside a set of parentheses to make sure we don't lose track of the idea that this negative out front is going to get distributed through every term in that function. Every term in that expression. All of that over h. From there, we'll expand out x plus h squared to get x squared plus 2xh plus h squared minus 5. And then again, we'll distribute that negative through, so this will become minus x squared and plus 5 all over h. Once we've expanded everything out, distributed that negative, now what we should see are some terms that will cancel. In this case, our x squared terms cancel, our constant terms cancel, and we're left with 2xh plus h squared all over h. If we look at the numerator, we can hopefully recognize that we have a greatest common factor. We can factor out an h, which will leave us with 2x plus h all over h. And then what happens is the h in the numerator and denominator will cancel out, since anything divided by itself is 1. And we're left with 2x plus h as the final simplified expression from evaluating that difference quotient. In every problem that we see, this step should happen where the denominator cancels out, so that h in the denominator should cancel out with an h in the numerator. If that's happened, you know you're on the right track. And we have, call it a modestly simple expression left over, relatively simple expression left over. But these problems take some work, again, especially with the introduction of additional variables, but with practice, hopefully they'll feel more comfortable.